So let me go ahead and get started. I want to start off by telling you I have placed a new link in our module for this week, and I made this week available, which is what I normally do on Tuesday, either Tuesday mornings or Tuesday afternoons. There is now a new week, and that new week is week 7, I'm pretty sure. Let me double check. Yes, week 7, February 24th to March 2nd. And what you'll see is there's the very first link under the optional videos is Gauss's law examples with extra examples after students left. The point of that is that once I finished teaching my lecture yesterday online, I had done quite a lot, but there was two more examples I wanted to work out, so I put them at the end after everybody, of course, had to leave. So it's been recorded and it's there. I want you to watch them. I think between that and the extra time I spent on Gauss's law covering and then recovering it, I think that's more than sufficient for the uh, execution of chapter 22. Not to mention the fact that later when we start capacitance, as well as in this chapter, chapter 23, we'll be using Gauss's law again. So you'll see more options of us using that. So make sure you check out that video. But we are going to go ahead and start into chapter 23, which, as I said, was electric potential. So let me start off by sharing my iPad screen. Hopefully everything works out right like it's supposed to. Yep, it's working so far. So you should notice I've taken a little bit of time to go ahead and start writing some fundamental things down that we'll need and you'll need to understand. So this is chapter 23, electric potential. The first thing we need to understand is in the 241 course, we actually gave you a mechanism, and I told you at the time, but I know as a student when I got finished with it, I didn't necessarily understand that and put all that together until long afterwards. So I'm guessing y'all might have run into the same problem, but basically, the point is, if a conservative force exists, and we talked a little bit ad nauseum on Physics 241 about what a conservative force was, there was these various statements that were all equivalent, which basically meant that if one of these is true, then all of them are true, and they included that F is a conservative force. The curl of F is identically zero. The integral from A to B of some scalar potential is independent of the path taken. It's only a function of the potential before and after, or at the beginning and the end. Basically, specifically, the final potential minus the initial potential, and it doesn't depend on path. So that's some of the stuff that we were actually doing, and of course, that all hinged on us having a potential energy, and that potential energy was due to the existence, excuse me, of a conservative force. So you can sort of think of the conservative force as belonging to the potential energy and the potential energy belonging to the conservative force. So that's something you want to keep in mind as well. But what we learned was that the change in potential energy is equal to the negative of the work done by the conservative force. So that's literally like a prescription telling you exactly how to find the potential energy once you found a force that you suspect is conservative. So once you find a conservative force, all you have to do is calculate the change in. Excuse me. All you have to do is calculate the change in potential energy by calculating the work done by the conservative force and going from some initial state to some final state, and then taking the negative of that work, and that's your potential energy. From that, you should be able to recognize a function. And to do that, of course, you need to remember what work is. And remember, work was actually defined to be what we call a line or path integral. Work is equal to the integral of f dot dl. And in this context, we don't generally use F. We normally use the electric field, and the electric field gives us the force by multiplying Q times the electric field. So we ended up getting the work is equal to the integral of Q E dot dl. So that's where we're starting now. And with that in mind, I need to give you that idea, but I also need to let you figure out what the electric potential is. So we're going to define the electric potential. To do this, your book starts off with a nice diagram of a parallel plate capacitor. And by the way, the parallel plate capacitor was one of those examples I put at the end of that video that I just showed you the link for, or just told you about the link for. I apologize for yawning. I don't know what's going on. I've been pretty much yawn free for most of the semester. But let's draw this parallel plate capacitor. So what we're imagining is that we have a series of positive charges on a single plate and then some distance away, and this is supposed to be a small distance away, meaning the distance, at least dead center, the distance between the plates is at least a factor of 10 smaller. At least a factor of 10 smaller than the distance from the center to the edge of the plate. So either the top edge, the back edge, the front edge, or the bottom edge is 10 times farther away than the middle is to each other. So that's sort of our plan. The other plate, of course, has the exact same charge, only it's negative. So notice I'm even trying to make sure I write a negative charge for each of the positive charges. Now, if you imagine a positive point particle right there up against, almost touching the positive plate, we'll say that's position A. And then what we're going to imagine doing is moving that charge to the other side, and in so doing, we'll now be at position B. So we're moving it from E to B. Now, the work done is, if we calculate the work done by the conservative force, we're going on the assumption, uh, excuse, we're going on the assumption that the Coulomb force, which led to the actual electric field, Coulomb's law, and since the Coulomb force looked identical to the Newton's law of gravity, and Newton's law of gravity was found to be conservative, it seems reasonable that we'd expect the electric field to be conservative, but we could go ahead and run those tests, which all you do is have to do one of them. The one that I would most likely try is calculating the curl. The curl of the electric field should be zero identically, and that means it's zero, period. It's not zero just when you put in a certain value of x or a certain value of y or a certain value of z. It's identically zero. If you found that to be the case, then you would know it's conservative. And I'm here to tell you that it is conservative, so you can check that on your own, or you can just trust me for right now because that's really all that's required of you in the 241, 242 level course. But what we're going to try to do is think about the work being done. Now, the conservative force is the electric force, and it would tend to make the positive charge run away from the positive plate, and therefore, uh, you would get a negative work done in moving from the positive plate to the negative plate with the positive particle if you're calculating the work done by the conservative force. And in this case, the actual conservative force, which is Q times the electric field, this electric field is in fact conservative. And not only that, we showed last time that the electric field inside or between the two plates was sigma over epsilon naught, which is a constant. The sigma is the charge per unit area on the positive plate, and the negative of the charge per unit area on the negative plate. And of course, epsilon zero is also a constant. So clearly the force is a constant, and it's actually exactly parallel to the path that we're taking. So when we calculate the work done by the conservative force, we would expect that to be a negative amount of work because the actual particle is going to be more comfortable next to the negative charges than it would be the positive charges. And of course, that electric field is just E, and the charge is just Q. So we have Q times E, and this is what I refer to as E, times the separation between them, and we're calling this separation between them D. Now, the work done by the conservative force, as I argued, had to be the negative, had to be a negative because this is something that it would do on its own. The force is actually compelling it to go this way. Now, if you actually know that would be a positive amount of work, scratch that. Uh, so it's that. And the way you could actually compute that is this. You'd say work is equal to integral of the charge Q, which is what I'm going to say this charge is. Okay, that's the charge Q. So we're going to say the electric force is Q times E, and of course that points in the positive X direction if I go on the assumption that this is the positive X direction. And this is the origin right here, which means this part is the y-axis. So basically it's QE pointing in the I hat direction. Ooh, I should write that in blue still. So it's QE pointing in the I hat direction. And then that's going to be dotted with the differential line element that's parallel to the x-axis. Therefore, that line element is dx I hat. Now, remember, when we do a line integral or a path integral, we either choose the differential line element to point in the direction of the travel, and then we just take the integral from small variable to large variable, or we use the limits of integration to say which way we're going, and we just point the dl in the positive coordinate direction, one of the two. So what I'm going to say is I'm going to argue that we actually use the dl to indicate the direction, and the direction is clearly positive, so I'm just going to write that like that. And then by doing that, I also have to take and just make my integration limits go from small variable to large variable. So the small variable is x equals 0, and the large variable is x equals d. So it's going to be an integral from 0 to d of QE dx I hat time, and of course there's a dot product. So the way that dot product works out, by the way, is we're going to say this is equal to, since the Q and the E are constants, they can come out in front. And since the dot product is what we call a linear operator, that means we can take all the scalars that are in front of the I hats or J hats or whatever, all the things that are not part of the vectors but are scalars multiplying the vectors, we can pull them out to the left of the dot product and just let the dot product work on the vectors themselves. So making that change, which included putting the QE outside of the integral and the dx in front of the dot product, gives us the integral from 0 to d of dx I hat dot I hat. And of course, the magnitude of I hat is 1. The magnitude of the other I hat's 1. The angle between them is 0, and the cosine of 0 is 1. So I hat dot I hat is equal to 1. And we're finally left with basically Q times E times D is the actual work done. So that's the work done by the conservative force. Now, what we're supposed to interpret that as is that the potential energy, delta U, is equal to the negative of the work done by the conservative force. So if you look at this, you can say, okay, well, this would be negative Q times E times D, and that means U final minus U initial is equal to negative Q times E times D. And we could figure out from that, because we're allowed to, of course, put the zero of potential energy anywhere we want, we could say that this is equal to basically a 0 as the final potential energy minus a Q times E times D. and I'll put that in parentheses. You'll see why in a second. For the initial potential energy, uh, I don't know. I think that doesn't work out so well. Let's see. We could call that potential energy final, but then that does an odd thing with the D. So, yeah. Uh, Either way, the main point here is we can see that our potential energy function U for this particular thing is some U of X is equal to Q times E times X in some sense. And that's basically what it is. That's our potential energy function. We can see here that the fact that the work of the conservative force compelled the positive particle to move from the positive plate to the negative plate told us that the total uh, or excuse me, told us that the work would be done on its own spontaneously. So it had to be a decrease in potential energy. That's why we got a negative change in potential energy. Specifically, the final state is at a lower potential energy than the initial state. Uh, with that in mind, let's see. I'm still trying to think of how I could have broken that up, the UF and the U minus, the U initial, such that we get the negative QED, but that is the actual result. So I'll just leave that for right now. You can feel free to think about it and try to work it out. But the main thing is that is our prescriptive method. We are going to repeatedly, whenever we run into a conservative force or a force that we suspect is conservative, we'll use those that identity that I or that theorem that I gave you in 241, and your book sort of mentioned bits and pieces of it in the 241 section. We can use that to establish whether or not the force is conservative. Once the force is conservative, then we can use the rule that says the change in potential energy is equal to the negative of the work done by its conservative force, where I'm saying it's because the conservative force has associated with it a potential energy, and they're sort of a pair, if you will. Okay? So that is what the potential energy function will be. And in fact, we're going to go a little bit further and we're going to define something that turns out to be more helpful. So we can work in the potential energy realm constantly when working with electricity and magnetism, but over time we've discovered that that is not necessarily the cleanest or easiest way to work. In fact, there's uh, a lot more results that make better sense in light of the equations that we have and are more easily expressed if we use something that's slightly different from the potential energy. What we call that something that's slightly different from the potential energy is the electric potential. So we define the electric potential as the potential energy. Now, as the potential energy per unit charge. Now, that might seem odd. Why are we doing that? But remember, when we went from F, I'm going to write this up to the left of the, well, I'll write it right below. I think I can fit that. So we went from F, which was Coulomb's law, which said that we had K, Q1, Q2, over r squared. We went from there to the electric force or the electric field by taking the force per unit charge, which of course became K Q1 over r squared. And I don't know why it keeps erasing that, but that's a very typical thing, evidently. It seems somewhat reasonable to talk about things not in terms of what we're used to, but in terms of what we're used to divided by Q. So what we get from that is we're going to say U, the potential energy, U sub A, the potential energy at A, is actually, or excuse me, let's do it another way. I'm going to define, instead of defining the potential energy, I'm going to define the electric potential. So the electric potential at point A is the potential energy at point A divided by the charge that you're dealing with. So that Q up there that we just did for this previous problem, that is the Q that we'll be dividing it by. Similarly, we have the
Yeah.
voltage at B would be UB over Q, and so on and so forth. So if you want to think about it that way, then you can go ahead and make a more grandiose statement and you can say, for instance, the voltage between B and A is equal to the change in voltage. Notice I just switched from the wording of electric potential to voltage because it turns out we're actually measuring something in volts. This electric potential is what we call voltage. So it's very normal for me to say that, not even realizing that I'm saying it before I told it to you. So that's why I'm telling it to you now. The electric potential energy per unit charge is called the electric potential, which we also call the potential and we also call the voltage. Okay. If it has the word energy in it, though, it has to be potential energy and have units of joules. This, on the other hand, is going to have units that are different, and I'm going to tell you what that is. But what we're saying here is the voltage from going from A to B is the change in voltage delta V. And remember, delta V always means final minus initial. So in this case, we're saying VB minus VA. Now, normally what I do when I subscript a potential with two letters, I normally put an arrow and the arrow points from the initial to the final. So I would have written this one as A with an arrow pointing to B and then B as a subscript. They wrote VBA, so I'm trying to show you both what the book does as well as what I do. Both are acceptable. But what we just learned is that these potentials are in fact equal to the potential energy per unit charge. So you could say UB over Q minus UA over Q, which gives me UB minus UA, oop, that's a lowercase a, divided by the charge Q. And that, of course, the change in potential energy is the negative of the work done by the conservative force, and then divide that by Q. So from that, we've now figured out yet another formula for the change in potential energy, or excuse me, the change in electric potential. And that formula is delta V equals the negative integral of E dot dl. So notice what happened by dividing by Q. Remember, we had the work was equal to Q times E dot dl. And when I divided by Q, that got rid of that Q. So now I have the delta V is equal to the negative integral of V dot D of E dot dl. And that's an integral from A to B. Okay. Now, this also gives us another thing that we can realize. For instance, the change in potential energy, which is the potential energy final minus the initial potential energy, that has got to be equal to, if we solve the expressions in the line above for the potential energy, we'd see that the potential energy is Q times the voltage. So we'd say this is Q times VB minus Q times VA, which is just Q times VB minus V. Actually, I didn't leave myself enough space there. It's Q times VB minus VA, which you can write as Q times delta V. So that's another expression, and that's actually going to lead us to a unit as well, a new unit for energy that we're going to talk about in a second. So this right here is a super important progression that you need to sort of understand This is a super important result that you're going to use frequently. And this right here, at least the two end parts, are something you're going to use repeatedly as well. So those are things that you need to know. And if you look at the equation sheet that you're allowed for this 242 course, you'll see some form of these everywhere. Okay. Now, for starters, we're going to work on talking about the units of this electric potential. So this is the electric potential. So that's the electric potential V that we're talking about. And the units of the electric potential are obviously the units of the potential energy divided by the units of charge. Well, the units of potential energies is joules, and the unit of charge is coulomb. And we've gone a little step further and went ahead and defined this unit. 1 joule per coulomb is defined to be 1 volt. And of course, the abbreviation for a volt is just a capital V, so we can also write this as 1V. So that's something that's helpful. We now know, for instance, that a joule per coulomb is a volt, and that's exactly the volt that you guys already heard about in lab when we did Ohm's law. So we already have some familiarity with voltage, but this is where that came from. Now, in addition to that, we found a new unit for energy. This new unit for energy is going to be called the electron volt. So, new energy unit. As you can see, the units of the potential energy, which are the units of the energy, are equal to the units of charge times the units of voltage. Well, that turns out to be obviously joule or coulombs times joules per coulomb, but that's not really the relevant thing. We're going to say, instead of this, we're going to say that 1 electron volt. Now, I drew that in a very specific way. That E drawn like that is sort of the special E that they frequently use to represent the charge of an electron. And then that capital V is the unit that we use for the volts. 1 electron volt is defined to be 1.602 times 10 to the negative 19th coulombs times 1.00 volts, which of course equals 1.602 times 10 to the negative 19 joules. So what we have is this new energy unit, 1 electron volt, which is equal to 1.602 times 10 to the negative 19th joules. And that turns out to be a unit that's much more helpful when we're talking about things at the microscopic atomic level. So that's a common energy unit that we'll use. And it literally is the unit, for instance, it's the amount of energy that an electron gets by going through a voltage difference of 1 volt. So literally 1 volt, 1 electron or 1 proton, since they have the same charge, if they go through a potential difference, meaning a potential electric potential difference. If they go through an electric potential difference of 1 volt, then they will have an energy equal to 1 electron volt. If they, on the other hand, go through 5,000 volts, then it would be a 5,000 electron volt or 5 kilo electron volts. So that's why it comes in so handy. It's just quick and easy math that you can do, and it eliminates, the need to multiply by 1.602 and all that crazy stuff. Anybody have any questions on that? Now, your book does give you in table 23.1, it gives you some typical voltages that occur in everyday life. Sort of. I mean, not everybody deals with this stuff, so they don't think that much about it. But for instance, the thundercloud to ground. What we mean by that is if you had some ability to take a voltmeter like you've been using in lab and jab the negative in the ground, say, and touch the positive into a cloud, then that would read on the order of 100 million volts. Okay, 10 to the eighth volts. That's 100 million. So that's a pretty important thing, but that is in fact the very voltage that causes lightning to strike. You can have, well, actually, you've probably heard they have ground to cloud lightning and cloud to ground lightning and cloud to cloud lightning and inter cloud lighting or intra cloud lightning. But all of that is driven by a voltage difference. High voltage power line, this is the ones that you see going through country fields on those big tall towers that sort of look like armless people without any heads. You know, those big towers, and they got sort of a little stub of an arm on each side, and wires are going right through their body as well as hanging off the little stumps of arms they have, and they have no head. Those lines, we've discovered that it's way more efficient to deliver electricity through lines like that if we raise their voltage up super high. And by doing so, we waste a lot less electricity and therefore pay a lot less for our electricity bills. Those lines, in order to do that, are on the order of 100,000 to a million volts. So that's why the table 23.1 suggests that high voltage power lines are 10 to the fifth to 10 to the sixth volts. Automobile ignition is on the order of 10 to the fourth volts. That's more on the starter side because of course, the battery is generally 12 volts. The ignition is the more or less the spark that gets it started. So you can sort of think in terms of a gas engine. You can sort of think of what kind of voltage difference you'd need from one part of the spark plug to the other to make the internal combustion cylinder in there explode with gas in it. A household outlet, you're probably familiar with that. They call it 120. Some people call it 125. That's ballpark of what it is, and it's pretty consistently around 120 to 125. Technically speaking, that is not, for instance, electricity is what we call AC when it comes out of your wall outlet, but that 120 figure is not the peak. It's not the amplitude, so it would go up to 120 and down to zero and then back to negative 120. That's not it at all. It's also not the peak to peak. It's not going from positive 60 down to negative 60. That's not it either. It's actually what we call the root mean square, which you've learned a little bit about already. But basically, if you calculate the root mean square of the sinusoidal AC current or sinusoidal AC voltage, I should say, you'll find that comes up to be around the 120 mark. It's basically the peak to peak voltage divided by the square root of 2. The automobile battery, like we said, is 12 volts. AA, AAA, C batteries, D batteries, all of those are 1.5 volts. That's their nominal voltage. But when you actually buy them, it's much more typical that they might read 1.72, maybe down to 1.68. That's normally what they start off as. And as they get more and more used, it's almost as if they have some internal resistance so that the terminal voltage drops from the 1.72 down to 1.65, down to 1.6, down to 1.58, 1.55, and even down to 1.5. Once they get down to 1.5, they're only going to be good for a little while longer because they're starting to get lower than the nominal voltage. So you can still maybe run a flashlight, but it's not going to be as efficient or effective. So that's the general voltage for AA, AAA, C, and D batteries. They're all nominally 1.5 volts. Of course, the square ones that I like to put on my tongue to test, which obviously there's a reason for hygiene reasons for you not to do that with random batteries you find in stores. Not to say that I don't do that anyways, but yeah, if you do that, and I do recommend you trying it, but if you do it, try to do it with a clean one so you don't get some heebie-jeebies or something. But either way, that's a 9-volt battery. Okay, and you can really feel it. You can feel it tingle your tongue quite a bit, and it tastes sort of metally. The resting potential, meaning the electric voltage from one end of a nerve membrane to another, or maybe even from one of the tendrils of a nerve ending to another tendril, is on the order of a tenth of a volt. And the EKG and EEG voltages through your skin, the ECG slash EKG are the ones that you put on your chest to read your heart beat basically. And then the EEG is the electroencephalogram, and that's for reading your brain waves. But both of those are electric potentials at the skin level, and those are on the order of a tenth of a millivolt, so 10 to the negative fourth volts. So again, that just gives you some ideas of what relevant voltages are. Let's look at a conceptual example 23.1. It says a negative charge. Suppose a negative charge, such as an electron, is placed near the negative plate in figure 23.1. In other words, that same figure I just drew for you on the previous page, we're now going to imagine a negative charge being put near the negative plate. So we're going to say, imagine this. Imagine this is a, well, I guess I drew closer to a square than to a circle on that one. Okay. And we're going to do it again over here. So this, in fact, is a negative charge at B and then a negative charge at A. Now, in this case, they say suppose a negative charge, such as an electron, is placed near the negative plate, as shown below. If the electron is free to move, will its electric potential energy increase or decrease? So, again, notice they use the word energy here. So when you use the word difference, you got to watch out. It seems like you could be talking about voltage, but if they don't explicitly say the word energy, then you know they're talking about electric potential and therefore voltage. If they do say the word energy, they're talking about the thing that's measured in joules or maybe even electron volts. So in this question is asking, is the electron free to move? Will its electric potential energy, if the electron is free to move, will its electron potential energy increase or decrease? Now, part of this should be answered from your knowledge of potential energy because that's the kind of energy we're talking about here. What do things do on their own? Do they go to an increased potential energy naturally, or do they go to a decreased potential energy naturally? Anybody recall? I saw that you were asking about the bottom equation. Uh, was it this one that you're looking at, or were you looking at the other page? No, it had to be this one. Okay. That was really close to the thing. It was really close to the edge, and the R wouldn't, it kept erasing it. So that was kind of weird. All right, so there's the bottom for those of you. I just saw the chat there. And yes, Alex said the potential energy decreases. That's exactly right. Potential energy naturally decreases on its own. It's sort of like the second law of thermodynamics when we were talking about something happening spontaneously. Potential energy can spontaneously decrease. Okay. So in this case, when we're looking at the negative particle, it's initially at the negative side, and that's really uncomfortable for it. It's not, I mean, to us, it's like the turtle sitting on top of the fence pole. A turtle sitting on top of the fence pole is not comfortable, right? And it's supposed to be part of a cruel joke that I hope nobody ever implements. But basically, you can imagine putting a turtle sitting on top of a fence post because his legs can't reach under him far enough. He then can't get off because he's on the bottom of his carapace or the breastplate of his carapace, if you will. Uh, so that's a whole, another sick thing. But the main thing is potential energy is proportional to height. So him being on top of a fence post means he has more potential energy than he does at the ground. But if he could shake it just enough, then he would fall and hopefully safely fall and land to the ground. That means he would spontaneously go from high height to low height, which means high potential energy to low potential energy. Well, the electron's going to do the same thing, except this time the height is indicated by its proximity to a negative charge. So an electron near a negative charge is just as uncomfortable as a turtle or a human sitting on top of a telephone pole. So it's going to run away from that naturally. So it will naturally decrease its potential energy. If you then go about thinking about, well, what would the actual change in voltage be? What you would realize is that the change in voltage, because of the change in potential energy being equal to the change in, or excuse me, because of the change in voltage being equal to the change in potential energy per unit charge, you'd have to divide that by a negative charge, and that would mean that the electron goes from low voltage to high voltage. So that's the whole picture with regards to conceptual question 23.1. So conceptual. Oops. 23-1 was the number. What we discovered was the E minus will spontaneously run from the negative plate to the attractive positive plate. Therefore, oops, therefore, the potential energy spontaneously decreasing implies that the negative plate was a place of high potential energy and the positive plate was a low potential energy place for the electron. And again, that's because, well, that's just naturally how it has to be, but it's partly because of the fact that the electron's a negative charge. Now, since, well, I should make this a capital, since delta U is equal to delta V over Q, and delta U is less than zero, then delta V would be greater than zero. And that's because the uh, dividing a negative number by another negative number makes a positive number. So the delta V is going to be positive, and therefore E minuses, electrons, move from low voltage to high voltage. Positive charges, of course, do the opposite, and that's sort of the problem with what we call conventional current. So, Ben Franklin had a 50-50 chance of choosing rightly. He ended up choosing the worst chance. So, what we ultimately discovered was that the charges that he thought would be doing all the moving and were positive turned out to be wrong. It was actually the other charges, what that he called negative, were the ones doing all the moving. So, what we picture in our circuits in everyday life, far as conventional current goes, is a battery or a power source having a positive side that's indicated by red on the power source, or the little nipple on top of the double A or triple A or D or C battery. That nipple up top, or that red part on the power supply, is the positive voltage in, and the negative voltage in is the other end. So the black side on the power supply, or the little dent at the bottom of the AAA, double A, C or D battery. Uh, when you have that set up, we picture as if there's positive charges running from that red positive voltage, or from that nipple, to the black voltage supply node, or the underside of the double A, triple A, or C or D battery. But in reality, it's not that. In reality, it's the negative charges running away from the black terminal, or the flat side of the battery, going towards the positive side, or the positive nipple, or the red side. Okay, so that's another thing to keep in mind. The good news is that you can just picture everything as conventional current. Imagine positive charges moving the way that you expect them to move. The only instant in which that becomes a problem is when you're studying something called the Hall effect. And basically, what you could do is you could set up a magnetic field and allow a current carrying wire to run through it. And if the positive charges are the carriers, then they would deflect to one side. Whereas if the negative charges are the carriers, they would also deflect to that same side. So you're either going to get a high voltage on the top and a low voltage on the bottom, or you're going to get a high voltage on the bottom of the wire and a low voltage on the top of the wire. The results would tell you whether it's a positive charge or a negative charge carrying the doing the moving. And what we discovered in that Hall effect experiment is, in fact, that the negative charges are doing the moving. So, any questions on that? All right. So let's look at example 23-2. Now it says, suppose it's called electron in a vacuum tube. Suppose an electron is accelerated from rest through a potential difference of VB minus VA equals VBA equals positive 5,000 volts. And then they have a little drawing. I'll show you that drawing. You can look at it, of course, yourself. A, what is the change in electric potential energy of the electron? B, what is the kinetic energy? And C, the speed of the electron as a result of this acceleration. So, what we have here is we're imagining that there's a negative plate from which electrons are running. So, we have here a negative plate, and negative electrons, of course, are running this way towards another plate. And this plate, in fact, is going to be a positive plate, but dead center it's going to have a hole in it. Because it has a hole in it, and the symmetry of the situation, the electron's not going to be compelled to move up any more than it's compelled to move down. It's not going to be compelled to move to the right any more than it's compelled to be moved to the left. So it's going to go on a straight line, but it's still going to be attracted so that it goes right through that hole. And what we're saying is the voltage difference between here and here is 5,000 volts. Okay. And in fact, what we'd have to interpret that as is this is the high voltage in, the positive side's the high voltage normally, and this is the low voltage. So they want to know, what is the change in electric potential energy? So A, delta U is question mark. B, what is the kinetic energy? So K final is question mark. And then C, what is the final velocity? Okay. Solution. What we know is delta U is equal to Q times delta V. Now, remember, we're going from low voltage to high voltage, so that's going to matter. We're also going to make use of the fact that kinetic energy, or more specifically, conservation of energy, delta U plus delta K is equal to zero. And we're going to assume that this 5,000 or this 5 kilo electron volt electron is not relativistic, and therefore the typical kinetic energy formula works. And that kinetic energy formula is K equals 1 half mv squared. Uh, Generally, the rule is if it's less than a percent of the speed of light, then you should be fine. But once you start getting close to the 1% of the speed of light, then you need to start thinking about using relativity. There's actually other tests. It's more about the rest energy compared to the kinetic energy that most people use, but that's still a decent rule of thumb. So for starters, just go ahead and calculate for part A. Delta U is equal to Q times delta V. Well, Q is equal to negative 1.602 times 10 to the negative 19th coulombs. So that's a number you should have memorized by now, even though I do give it to you on your test material. So still, for the electron, it's a negative charge. For a proton, it's a positive charge, but both of them are 1.602 times 10 to the negative 19th. The change in voltage is the final voltage, which is plus 5,000 volts, minus the initial voltage, which is zero point 0.0 volts. So you see, we're going to get a delta V that is in fact positive, and then that's going to be multiplied by a negative charge. And when you do that, that's going to give you a negative number, which is what you expect. You do expect the electron to move in such a way that it decreases its potential energy. How much is basically 5,000 times 1.602 times 10 to the negative 19th? And that gives me negative 8.01. And really, remember, this 5,000, according to your author, is an ambiguous amount of significant figures. So I'll just assume that we can count on three. So that's going to be 8.01 times 10 to the negative 16 joules is the energy. Okay. Now that's the change in potential energy. So I'm going to say delta U is negative 8.01 times 10 to the negative 16th joules, which by the way is also equal to negative 5.00 kilo electron volts, just because that's a much nicer figure to use, isn't it? Okay. Now B, they want to know what is the final kinetic energy. So we know delta U plus delta K is equal to zero. That tells us negative 8.01 times 10 to the negative 16th joules plus delta K is equal to zero. And that means delta K, which is K final minus K initial, and K initial is zero, that delta K is going to be equal to 8.01 times 10 to the negative 16 joules, and therefore K final is equal to 8.01 times 10 to the negative 16 joules. But you could also call that 5,000 electron volts. Now for part B, and see, a student just came in. For part C, excuse me. For part C, they want to know the velocity. So we know that the kinetic energy is equal to 1 half mv final squared, and that's equal to 1 half times the mass of the electron, which is 9.109, times 10 to the negative 31st kilograms, and then V final is what we're looking for, and that's equal to 8.01 times 10 to the negative 16th joules. So if I multiply 8.01 times 10 to the negative 16th, if I multiply that by 2, and then divide that by 9.109 times 10 to the negative 16, excuse me, 10 to the negative 31, I get 1.75 times 10 to the 15th. And therefore, the velocity final is equal to the square root of 1.758. Actually, that's 1.759 times 10 to the 15th meters squared per second squared. And I'm pretending like we have three sig figs. That's why I underscored the 9. So I'm going to take the square root of this number, the 1.759 times 10 to the 15th, and that's going to give me 4.19 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th meters per second equals V final. Now, you'll notice the speed of light is basically 299,792,458 meters per second. And that's technically, let me erase that, that's technically to an infinite number of decimal places, meters per second. So you can see it's about 3 times 10 to the 8th meters per second. And lo and behold, this is clearly not even 1%. It's more like 10% of the speed of light. So it's not necessarily reasonable to use 1/2 mv squared on that one. Anybody have any questions on that? Okay, so I gave you a little bit more than just the what the example was asking for in both the 23-1 case and the 23-2 case. Uh, Now we're going to go on and understand a little bit more about what the actual voltage is, how to go about calculating it, that sort of thing. So let's look at example 23.3. It says electric field obtained from voltage. Two parallel plates are charged to produce a potential difference of 50 volts. If the separation between the plates is 0.050 meters, determine the magnitude of the electric field in the space between the plates. So that's example 23-3. And basically what we have here is, again, parallel plate. And the distance for this is 5.0 centimeters. And the electric field, since this side is going to be negative and this side's going to be positive. Someone else came in. Because of that, that means the voltage on one side is 0 and the voltage on the other side is 50 volts. So I'm going to say V equals zero point 0.0 volts, and I'm going to say uh, V equals 50.0 volts for this part. That means the electric field, remember the electric field is defined to point in the direction in which a positive particle or positive test particle would actually travel. So if we dropped a positive particle between these plates, we'd find that the electron would run that way. Therefore, the electric field is that way as well. Okay. Now, what we found earlier was that the potential energy and going across a voltage like this across between two parallel plates, because the electric field between the plates is a constant, the potential energy ends up becoming basically in magnitude Q times E times D. Okay. Now that means that the change in voltage, which is the change in electric potential energy per unit charge, that ends up becoming E times D. because we had to divide out the Q. So what we know, oh, and I wrote delta U, I said delta V, but I wrote delta U. So delta V is what that's supposed to be. Because of that, we can go ahead and say that the change in voltage, which is equal to 50, is actually equal to negative 50, technically, but the magnitude of it is going to be 50. We're going to determine the magnitude of electric field. Okay, so we really don't care about whether the particle's positive or negative going one way or the other. It's just a matter of us computing the strength of the electric field. So what I'm going to do is say the change in voltage, and I'll put it in absolute value bars so there's no confusion. The change in voltage is 50.0 volts, and only the 5 and the 0 are significant, and that is got to be equal to E times D. And of course, the D is 0.050 meters, and that means the electric field is in fact equal to 50.0 volts divided by 0.050 meters. Notice the fives are going to cancel out. And the bottom is actually 5 over 100. So we're going to multiply the 50 times 100. That would make 5,000. But then we're going to divide it by 5. So that makes 1,000. And technically, only the first two digits are significant. So the electric field here is 1.0 times 10 to the third volts. And you can see why we don't uh, strictly obey the scientific notation process and use, only the proper number of sig figs. It'd be much easier to just write 1,000 volts. Anybody have any questions on that? Oh, it's 1,000 volts per meter. Sorry about that. I completely left that unit out. I was thinking about the next line. But that's a key thing here. Remember, I told you that later we'll learn that the units of the the electric field, which we had treated as newtons per coulomb, I said they'll become something better. Now you can see that the units for the electric field are not only newtons per coulomb, the units for the electric field is also volts per meter. And that's a much more useful, in most cases, it's a much more useful unit. So note, so that's something to keep in mind. The units for the electric field is newtons per coulomb or volts per meter. Now we're going on to example. I still got plenty of time. We're going on to example 23.4. 23.4 says charge conducting sphere. Determine the potential at a distance r from the center of a charge conducting sphere of radius r 0 for A, r less than, or excuse me, r greater than 0, r 0, B, r equal to r 0, and C, r less than r 0. So they want to know the a distance r from a charged conducting sphere of radius r0, so v equals question mark, for r greater than r0, r equal to r0, and r less than r0. So that's our big problem here. Okay. Now, our solution to this is going to be, listing the equations that we're going to use. And for instance, one of the equations we know is the electric field caused by a spherical distribution of charge, which happens to be the exact same electric field caused by a point charge at the center of the spherical distribution of charge. The only difference is in between the center of the actual sphere and the actual edge of the sphere, that's not valid. We have to deal with the fact that the sphere is actually a conductor and it has a charge on it. So we've got to deal with that. But either way, what we know, at least for R greater than R0, we know that the electric field is going to be Q over 4 pi epsilon naught R squared. We also know that delta V equals the negative integral of E dot dl, and we're going to use that to calculate the voltage change. Now, if we think about potential energy, we know that there's a point at which you can just say, hey, this point in space is going to have zero potential energy. Well, guess what? We can do the same thing with this electric potential because it's so closely defined to the potential energy. It's literally only a factor of Q different. So we should also expect that we can arbitrarily define where the zero potential energy is. And when you're talking about a distance from a spherical charge distribution, it would seem reasonable to take the potential energy and therefore the electric potential energy as well and the electric potential and set it equal to zero at r equal infinity. So we can actually do that. Let me start by drawing a little coordinate system. Okay, so here's our little coordinate system, and this is our x-axis, this is our y-axis, this is our z-axis. Doesn't really matter too much, but the thing that does matter is we're going to have a charged conducting sphere of radius r0. I'm going to try to make that a little bit bigger, and then I'm going to try to center it up a little bit better. Okay, so there's the center, and we're going to say this distance is r0. Okay, that's the distance from the center to the edge. And what we're going to imagine is bringing basically, or imagine going from out to infinity and bringing ourselves into some distance r. So we can imagine that we're going to bring ourselves into this distance, which is r, and we're bringing that all the way from infinity. So when we do that, we're going to say delta V, which is equal to V final minus V initial, is equal to the negative integral of E dot dl. And from that, we can say delta V is equal to V final minus V initial equals the negative integral. Now we have the electric field, and the electric field is going to point radially outward. So we can go ahead and say that's going to be Q over 4 pi epsilon naught R squared R hat. Now remember R hat, if you take any point in space and you want to find out where what R hat is at that point in space, all you do is draw a line from that point in space back to the origin, and then you draw a unit vector parallel to that line but pointing away from the origin. Okay, so it'll be 1 unit long, and its base will be at the point that you wanted to draw the r hat vector. You'll put the tail of the r hat vector right there, and you'll move it 1 unit long and stick it out there. So in principle, for instance, this would be, for this point right here, that would be the r hat vector, because that line that it's parallel to goes back to the origin and it happens to point away from the origin, and we're going on the assumption that I've made that vector to be 1 unit long. Okay, so that's my E. Now, remember what I said about when we're doing path or line integrals, I either have to allow the DL to indicate the direction of integration, or I have to let the limits of integration do that. But I can't do both. If I do both, I'll end up getting like the negative of the right answer. So what I'm going to do is I'm going to say my path of integration is in the negative r hat direction. So I'm actually integrating from out there at infinity inside, and that means the dl is going to be negative dr r hat. Okay. But because I chose the DL to be the indicator of the direction of integration, that means I've got to choose my my range of integration to go from from low coordinate to high coordinate. Okay, it's just in the positive direction, in other words. So by doing that, I have to take this from low coordinate, which is r, to high coordinate, which is infinity. So that's the way that works. We could have done this by calling it drr hat, but then I would integrate from infinity to r. Either one of those should both give you the same answer. Okay. Now that we do that, I've got to use what I taught you about the linearity of the dot product, and I'm going to pull the constants out in front. So right now I have two negatives, the negative with the dr and the negative that's out in front, and I also have a q, a 4 pi, and an epsilon naught that are all constants. So I'm going to pull the two negatives, which makes a positive, and the q over 4 pi epsilon naught out in front. And now I'm going to integrate from r to infinity of, now here's the part where I use the linearity of the dot product. I'm just going to pull the dr to the left, and all I'm left with is r hat dot r hat, and that r hat dot r hat, as we saw with Gauss's law, is in fact 0, or excuse me, 1. Now we can integrate, oops, I left off something too. Notice I did write the dr, but I forgot to include the dr, the r squared under it. So let me fix that. I'm glad I did that and noticed it before we went further on. So what I have is the integral of r to the negative 2. And the integral of r to the negative 2 is negative 1 times r to the negative 1. So this is going to become negative q over 4 pi epsilon naught times, notice I put the negative out in front. That took care of the negative 1 over r being the integral. And now I got to evaluate this from r to infinity. Well, that means negative q over 4 pi epsilon naught. Almost done here. Now, the top range of integration is an infinity, and that means we have to take the limit as r approaches infinity of 1 over r, and then we have to subtract from that 1 over r because that's the range of integration. The r value is the second integral, the second range. So what we see here, the limit as of 1 over r as r approaches infinity is in fact 0. So we get a negative times a negative gives us a positive, and that means we get q over 4 pi epsilon naught r, and that is the actual voltage. So V equals q over 4 pi epsilon naught r for r greater than r0, and that's our part A. Any questions on that? All right. Now what we can do is we're going to go from there to r equal to r0. But before we do that, I want to go ahead and figure out what the actual electric field in it is. So we have to go and calculate the electric field within the sphere. I'm going to do that as well. So if you remember, we had this coordinate system like this, and we had inside of there a sphere, and I'm going to draw it a little bigger now so we can see it a little better. This distance is R0. And if we imagine putting a Gaussian surface just inside of it, that's supposed to be a sphere. So if we imagine putting a Gaussian sphere just inside, then we could use Gauss's law, which says the closed integral, whoa, Nelly, the closed integral of E dot dA is equal to Q enclosed over epsilon naught. And of course, the left-hand side is the closed integral E dot dA. And our hypothesis is that the electric field is E of R hat, and the dA is going to be just the dA for a sphere R hat, and therefore we get the normal E of R times 4 pi R squared, in this case, R being the radius of the Gaussian surface. Okay, so that's the left-hand side. The right-hand side, on the other hand, the right-hand side of Gauss's law is Q enclosed over epsilon naught. But as we learned for conductors, the electric field inside uh, ultimately results in all the charge being completely on the outside. So the charge enclosed is actually zero. So if you set the left-hand side equal to the right-hand side, you get E times 4 pi R squared equals 0. So you get E is equal to 0 for R less than R0. Okay. Now that we have that, we could also do the other thing for R greater than R0, and we would have gotten that expression that we already had, but that's basically it. Now that we're going to do that, we got 2 minutes left. Now what I'm going to do is calculate the change in voltage from R to R0. So delta V for part B, delta V is equal to the negative integral of E dot dl. And we already know that that is, of course, the integral of Q over 4 pi epsilon naught R squared R hat dotted with, again, negative dr R hat, and we're going to take it from, since I chose the direction by using my DL, I have to go from small r to big R, so I'm going to go from R0 to big R. And of course, this gives us negative Q over 4 pi epsilon naught integral of R to the negative 2 dr R hat dot R hat, which is 1. And this gives me, of course, positive Q over 4 pi epsilon naught R. Notice the negative is what made that come out to be a positive, but now we've got to evaluate it from R0 to R. And in this case, you can see, oops, I didn't mean to put that arrow in there. This case, you can see it's Q over 4 pi epsilon naught times 1 over R minus 1 over R0. And that's the change in voltage. And the initial voltage, of course, that's delta V, so that's V final minus V initial. We knew that V initial was Q over 4 pi epsilon naught R. Therefore, we can say that Q over 4 pi epsilon naught R minus Q over 4 pi epsilon naught R0 is equal to V final minus Q over 4 pi epsilon naught R, because that's what the initial voltage was. It was actually Q over 4 pi epsilon naught R. So now what we can see is that V final is equal to Q over 4 pi epsilon naught R0. With that in mind, uh, we can now consider what it is for r less than 0. And when we do that, this is for r less than r0. Delta v is equal to the negative integral E dot dl, but we already found out that the electric field inside of the uh, conductor is 0. So we know this quantity 0, and we know the v final is what we're looking for, whereas the v initial at the surface was at R0, and that's all got to equal this. So what we know is V final is actually equal to V initial, which is Q over 4 pi epsilon naught R0. So if we make a plot of voltage versus distance, we're going to get a quantity Q over 4 pi epsilon naught R0 that happens to be right here equal to R0. So from here on out, it's going to fall off like 1 over r, but then it's going to be a constant from there on out. So that's what the electric field looks like for this one. You guys are free to go. I ran 2 minutes over. I apologize. Of course, you're always free to go when it right time runs out. So please remember that. But I'll wait in case anybody has any questions. I'll leave only after the last person leaves. Thanks for coming, everybody. Jada or Alex, y'all have any questions?
I kind of have like just like a personal question
Okay.
towards the subject, but I know that you're studying Latin. Is there a reason why you're studying Latin? Is it for the subject?
I'm a nerd.
You're a nerd. Fair enough.
I've always wanted to learn Latin. I had Latin when I was in high school, but I was not a good student at that time. And later I found out my Latin teacher was actually a pedophile. He had filmed thousands of video hours of high school girls in the locker room. So although I had what
In
I
the
thought was a
world.
decent Latin instructor,
All right.
and by the way, he got off scot-free because they didn't use a search warrant. And when they found all the videos, they basically threw it out the course, out the
That's
court.
crazy.
Is he at least on a list?
Yes, but I did take some interest in it, and I love Rome. I love the idea of being able to read the Principia, so that's mainly why. Next, I'm
The Grand
doing
Canyon?
ancient Greek.
Is that Oh, you're good. You're good. Is the Grand Kipia? What is that?
That's Newton's book on physics.
Oh, okay.
He wrote it in Latin. It's actually a different Latin than I care about. I usually care about the ancient Latin, but this is sort of Renaissance Latin where they did have a J, and so they don't have a J in Latin, and the pronunciations are quite different. And they,
Cool.
since then, them and the Catholic Church have been making Latin a bigger language with more words. So there's like Latin words for television and stuff like that now. I don't care about that stuff, but I do care about the Renaissance era Latin that was used by Newton and Galileo and Kepler and those guys.
Right on. Cool. Yeah, no, I always wanted to ask, but I never had the time. Yeah, okay. Well, thank you
Yeah,
for the
I do
lecture.
about 30 minutes to 2 hours a day on my Latin.
Do you do Duolingo, I'm guessing, or no?
Duolingo is what I did for the first 2 years, in addition to reading Wheelock's Latin and
Hmm.
Oxford Latin and Cambridge Latin and some other stuff. But lately, I've been using something called Lingua Latina per se illustrata, which is Latin language through illustration by Hans Orberg. And that one's
Oh,
kind of neat. It's just a book that you read, and they never write anything except Latin. There's not a single English sentence in it, and you read it and you learn the words as you go along, and they teach you grammar as you go along. So that's what I've been doing. It's much more successful and a lot easier than my course using Wheelock's Latin and all that other stuff.
that is really interesting to, I guess, to think about that you're learning the language without knowing anything. and then
Yeah,
I just
it's pretty
get into it.
impressive. And not only that, there's an app called Legentibus,
Yeah.
Legentibus, and I signed up for that. And they bought Hans Orberg's stuff, so they actually read it all to me. So
Okay.
I've learned excellent pronunciation, as good as that guy's pronunciation is. There's one guy that sort of owns Legentibus, and he's really, really good. And I read using his voice, but I also read just on my own. But they have that book and all his other books, and then I bought all these manuals for learning to write it and stuff like that. So I'm learning it that way too.
Cool. Yeah, no, I definitely want to get more into the math field, but
Hmm.
also I'm into hospitality, I think
Right.
that's it. I just came back from a meeting from my I guess job, and we're trying to figure out how we can bring in, I guess, customers, and that made me think about I guess like liberal arts almost.
Yeah.
So no, that's really cool. Was it how do you spell the website that you're using again?
Legentibus,
Yeah.
Legent. It's actually an app,
Oh
and
yeah.
there's a website too, but it's
Okay.
Legentibus.
Cool, yeah.
I think I pay around $100 a year for that.
Yeah.
And they're actually writing another book in it. So I've actually read probably 30 some books in Latin now because of that Legentibus app. And one of them is a book they're writing in real time. It's called Alda, and it's takes place of a little German girl and her friend are out in the woods, and then a wolf comes up, and then three wolves come up, and then all of a sudden a strange dude comes up. Come to find out, it's her dad, and her dad's a escaped slave from a Roman captain, and it's just really an interesting, heart-wrenching story. But it's pretty awesome.
Well, thank you for your time and all that.
No problem. Check it out. I'm sure you'll love it. It's awesome, and
I'll
the
try to
book's
learn how to
dirt
read it
cheap.
first.
This
Okay.
is the actual book that they use. Let me kill this real quick.
Okay.
Yeah, so if you see that, it's Lingua Latina per Illustrata, Pars One Familia Romana. And I went and bought that, and then I bought the student manual that came with it, and I bought the Grammatica. All of these are completely in Latin. There's literally not a single English sentence in it. Well, that student one was. Then the teacher's book, so I can check my work, and then the exercise book, which is where I'm learning to do all the writing. So it's a lot of stuff. And if you looked at textbooks, a stack of textbooks like that would probably cost you $400 in most subjects. But with this book and this particular subject, I maybe have $130 total.
It's not that bad, especially for
Mm-mm.
that material.
Yep.
But
So yeah, enjoy it, man. It's awesome. But let me know if there's anything I can do to help you. And this is a matter of doing a lot of work and it's my notes that I take every day
oh
is
man.
learning to write and read in Latin. How about
Maybe I can
you,
get a class later.
Jada? Is that Jada there?
Yeah, I also studied languages, but I'm not nearly as disciplined as you. You said 2 to 3 hours or 20,
Yeah,
20
yeah.
to 30
I force myself to spend at least 30 minutes a day, but often I
minutes
spend 2 to 3 hours.
in
So I do
total
15
a
minutes of
day.
reading and 15 minutes of writing.
Wow, yeah, no wonder you're able to write so quick. Yeah, no, I feel like learning a language for me, it was more so hearing it to understand. That's the most issue I had with learning
Yeah,
Spanish.
when I was doing Duolingo, the fact that I was hearing it was making it a lot easier, but they didn't do anything to try to teach you the language. They just sort of threw sentences at you and
Yeah,
said,
oh yeah, that's
translate it.
exactly what they do. But reading is really helpful as well. I feel like that would help,
Yeah,
especially when on
absolutely.
paper. Yeah.
You should see all the notes I had from Duolingo. Man, I've got three notebooks full of notes from them where I literally did, I did a couple lessons every day, period. So,
Your handwriting looks great. I mean, it looks like you're writing cursive as
yeah, that's what
well.
I'm trying to improve my handwriting. It's really hard to write on the tablet though. That's why I'm forcing myself to do it so I can write better for you guys, even though I know most people aren't learning cursive nowadays. I figured they could probably
Um,
read it a lot easier than they could write it.
yeah, I agree. I agree.
But if I ever write anything in cursive and y'all have a hard time, just let me know. I will immediately write it. It's just so much slower to write in script than it is in cursive.
Hmm, yeah, I guess. I mean, well, maybe not for me because like my handwriting will probably just get poorer and poorer, but you'll still be able to read it, and it might
Yeah.
be.
when
Might
I
have wrote it
write in
fast.
script, I write each letter and it just
Oh yeah, me. I feel like I write in print and cursive like combined
yeah, you
sometimes.
sort of let the letters flow. I have not
Exactly.
been able to de-discipline myself enough to do that, which was horrible because it would look much better if I did.
Yeah, and had to write every single line. Um, but I also had a personal question. So
Yes. How can I help
go
you?